Oxygen is one of the most essential elements on Earth, without which life, combustion, modern industry, and medicine would not exist. Yet, despite its importance, oxygen is not actually manufactured in the way most people imagine. Humans do not create oxygen from nothing. Oxygen already exists all around us. The real task of industry is not to produce oxygen but to separate it, purify it, and concentrate it into a usable form. The air we breathe is a mixture of gases. Roughly 1/5 of this mixture is oxygen, while most of the rest is nitrogen, with small amounts of other gases. This means oxygen is everywhere, but it is never found alone. It is always mixed with other gases, and for industrial, medical, and technical use, it must be isolated to an extremely high purity. If you like similar educational content, please like, subscribe, and share the video with your friends. Every oxygen cylinder, every hospital ventilator, every welding torch, and every steel factory relies on the same basic idea. Oxygen is extracted from ordinary air. The challenge is that gases mix perfectly at the molecular level, which makes them impossible to separate using simple filters or mechanical sieves. Oxygen and nitrogen do not react chemically with each other under normal conditions, so chemistry alone cannot be used to split them apart. Instead, the entire process is based on physics. The key lies in the fact that different gases change their state at different temperatures. When cooled enough, gases become liquids, and although oxygen and nitrogen behave very similarly, they do not liquefy or boil at exactly the same temperature. This small difference is what makes large-scale oxygen production possible. Industrial oxygen production therefore begins not in a laboratory, but in the surrounding atmosphere. Massive systems are designed to take in huge volumes of air and subject them to carefully controlled pressure and temperature changes. The goal is to push the air into extreme conditions where its components can finally be separated. This process requires more than just cooling. Air must first be cleaned, compressed, and prepared, because any impurities would cause serious problems at very low temperatures. Only after these preparations can air be transformed into a form suitable for oxygen separation. At this point, the process stops being simple and becomes a carefully engineered sequence of steps involving high pressure, extreme cold, and precise control of energy. Oxygen production is not about creating something new, but about mastering the physical behavior of matter under extreme conditions. And this is only the beginning. Because before oxygen can be separated, air must first be compressed and purified to an extraordinary degree. Before oxygen can be separated from air, the air itself must be transformed into a controlled industrial input. Atmospheric air is far from pure. Along with oxygen and nitrogen, it contains water vapor, carbon dioxide, dust particles, and trace impurities. These components are harmless for breathing, but they become a serious problem when air is cooled to extremely low temperatures. The first step is drawing in large volumes of air using powerful industrial compressors. These machines gradually increase the pressure of the air far above atmospheric levels. Compression is necessary because it makes later cooling far more efficient and allows the air to reach conditions where liquefaction becomes possible. However, compressing air also causes it to heat up, which is a direct consequence of basic physical laws. For this reason, compression never happens in a single step. Instead, air is compressed in stages, and after each stage it passes through heat exchangers where excess heat is removed. This cycle of compression followed by cooling is repeated multiple times until the air reaches the required pressure and temperature conditions. Without this controlled approach, the system would overheat and become inefficient or even unsafe. Once the air is compressed, purification becomes critical. Water vapor and carbon dioxide must be removed almost completely. If they were allowed to remain in the air, they would freeze during the cooling process, forming ice or solid carbon dioxide. These solids would clog pipes, valves, and heat exchangers, potentially shutting down the entire system. To prevent this, the air is passed through specialized purification units that use adsorption materials designed to trap moisture and carbon dioxide on their surfaces. As the air flows through these materials, unwanted components are captured while oxygen and nitrogen pass through unaffected. These purification systems operate continuously and are periodically regenerated so they can function without interruption. After purification, the air is clean, dry, and compressed, consisting almost entirely of oxygen and nitrogen. At this stage, it is finally ready for the most demanding part of the entire process, cooling the air to temperatures so low that it can no longer remain a gas. Only when air reaches this state can its components begin to separate in a controlled and predictable way. And this is where oxygen production truly enters the realm of extreme physics. Once the air has been compressed and purified, it enters the most technically demanding stage of the entire process, cooling it to temperatures so low that it can no longer remain a gas. This step is known as cryogenic cooling, and it operates far beyond anything encountered in everyday refrigeration. Ordinary cooling methods are completely insufficient here, because the temperatures required to liquefy air are far lower than those used in food storage or industrial chillers. Instead of relying on external cooling sources, oxygen production plants use the physical behavior of gases themselves. The core principle is that when a compressed gas is allowed to expand rapidly, its temperature drops. This cooling effect occurs because part of the gas's internal energy is used to perform the work of expansion, leaving less energy available as heat. By carefully controlling pressure and flow, this effect can be amplified and reused again and again. The compressed air is routed through a complex network of heat exchangers and expansion devices. As it expands, it cools, and the cold air leaving the system is then used to pre-cool incoming air. This creates a self-reinforcing cycle where each pass through the system lowers the temperature further. Rather than wasting cold energy, the process continuously recycles it, making large-scale liquefaction possible without extreme energy losses. As temperatures continue to drop, the air approaches a critical point where gases begin to transition into liquid form. This does not happen all at once. Different components of air respond slightly differently to falling temperature, and these small differences are crucial. Nitrogen and oxygen have similar properties, but they do not behave identically when cooled. Their transition points are close, yet distinct enough to allow separation later on. Eventually, the air becomes a cryogenic liquid mixture. At this stage, it must be handled with extraordinary care. Cryogenic liquids are extremely cold, and any unwanted heat entering the system can cause rapid boiling, pressure changes, and instability. For this reason, the liquid air flows through specially insulated pipes and vessels designed to minimize heat transfer from the surroundings. This moment marks a fundamental transformation. Air is no longer an invisible gas, but a tangible liquid that can be processed and separated. Only now do the physical differences between oxygen and nitrogen become fully exploitable. With the air in liquid form, the stage is set for the actual separation process. Because turning air into liquid is only preparation. The real separation happens next. Once air has been transformed into a cryogenic liquid, the actual separation of oxygen can finally take place. This is done using a process called fractional distillation, which relies on the fact that different substances boil and condense at slightly different temperatures. Even though oxygen and nitrogen behave very similarly, their boiling points are not identical, and this small difference is enough to separate them on an industrial scale. Liquid air is fed into a tall distillation column designed to maintain a carefully controlled temperature gradient from bottom to top. The lower part of the column is slightly warmer, while the upper part is colder. Inside the column, liquid and vapor are constantly interacting, flowing upward and downward at the same time. This continuous exchange is what allows separation to happen gradually rather than all at once. Nitrogen has a lower boiling point than oxygen, which means it tends to evaporate more easily. As the liquid air warms slightly inside the column, nitrogen begins to vaporize first and rises upward. Oxygen, which requires a higher temperature to boil, remains in liquid form longer and settles toward the lower sections of the column. Over many repeated interactions, nitrogen becomes increasingly concentrated near the top. while oxygen becomes increasingly concentrated near the bottom. The column is filled with internal structures, such as trays or packing material that maximize contact between rising vapor and descending liquid. Each interaction slightly improves purity, removing traces of nitrogen from the oxygen-rich liquid below and traces of oxygen from the nitrogen-rich vapor above. This process repeats dozens or even hundreds of times within a single column, producing very high purity products. By the time the separation is complete, nearly pure nitrogen exits from the top of the column as a gas, while high-purity liquid oxygen is collected near the bottom. The system operates continuously, with fresh liquid air constantly entering and separated gases constantly leaving. Precise control of pressure, temperature, and flow rates is essential, because even small disturbances can reduce separation efficiency or product purity. At this stage, oxygen has been successfully isolated from air, but it is still in a cryogenic liquid state. While liquid oxygen is extremely useful for large-scale storage and transport, it is not always the form needed by end users. Depending on its final application, oxygen may need to be stored as a liquid, converted back into a gas, or delivered directly through pipelines. Separation is complete, but oxygen is not yet ready for use. Once oxygen has been separated from liquid air, the production process is technically complete, but its journey is far from over. Oxygen is a highly reactive substance. It does not burn by itself, but it dramatically intensifies combustion, which means it must be handled with great care. The way oxygen is stored, transported, and delivered depends entirely on how much is needed and where it will be used. In large industrial operations, oxygen is most commonly stored in its liquid form. Liquid oxygen occupies far less volume than gaseous oxygen, making it ideal for large-scale storage and long-distance transport. To keep oxygen in a liquid state, it must be maintained at extremely low temperatures. This is achieved using specially designed cryogenic tanks with thick insulation that minimizes heat transfer from the environment. These tanks are not actively cooled. Instead, they rely on insulation to slow down heat flow. A small amount of oxygen continuously boils off, which is normal and carefully controlled. For smaller users such as hospitals, laboratories, or workshops, oxygen is often stored as a compressed gas in high-pressure cylinders. In this form, oxygen is kept at very high pressure, allowing a significant amount of gas to be stored in a relatively compact container. These cylinders are equipped with precision valves and regulators that allow oxygen to be released safely and in controlled amounts. Strict safety standards apply to their design, handling, and inspection. Transporting oxygen depends on its form. Liquid oxygen is typically moved using insulated tanker trucks that function as mobile cryogenic storage units. These vehicles supply steel plants, chemical facilities, and medical oxygen distribution centers. Compressed oxygen cylinders, on the other hand, are transported individually or in secured bundles to hospitals, construction sites, and industrial workshops. Oxygen plays a critical role across many fields of modern civilization. In metallurgy, it is used in steel making to remove impurities and increase efficiency. In welding and cutting, oxygen enables extremely high temperatures that make it possible to shape and join metals. In the chemical industry, oxygen is a key reactant in numerous production processes. In medicine, oxygen is literally life-saving. It is essential for anesthesia, intensive care, emergency treatment, and long-term respiratory therapy. Medical oxygen must meet especially strict purity standards, and its supply systems are designed to be redundant and highly reliable. Oxygen is also crucial in aerospace and space exploration. It supports breathing for crews and acts as an oxidizer in rocket engines, allowing fuel to burn even in the vacuum of space. In these applications, purity, stability, and precise control are absolutely critical. From ordinary air to cryogenic liquid and finally to controlled delivery, the entire oxygen production chain is a remarkable example of applied physics and engineering. Nothing is created from nothing. Instead, nature's raw materials are carefully separated, refined, and transformed into forms that modern technology can safely and efficiently use. Oxygen production is not just an industrial process, It is one of the invisible systems that makes modern life possible.